Hello students. So this is your science teacher from Northeast Academy. So today we will be starting with chapter 12, that is electricity, part of physics basically. Quite interesting chapter. So before commencement of the classes, let me inform you few of the basic systems which you must follow. See, all of you are in your house only, right? Most of you probably are losing the habit of regular studies and all. So I will be assuming that you people are in front of me only. Although these are not going to be our live classes, the classes will be recorded in the school only. So whatever the classes we will be uploading, whenever you will be going through the lectures, please sit in a chair and a table and make some proper notes from the class. For the note making, you must have a white copy. Okay, the copy has to be what? White copy, and you should have at least two colored pens. That is, one is blue, another should be black or red. That is up to you people. Okay, so these are the simple rules that we must follow to ensure the most out of our lectures. Okay, so let me give you a study map of that particular chapter, electricity. Okay, so what we are going to study in this particular chapter, we will first try to understand what is an atom. Okay, thereafter from that atom we will be try to understand what is charge. Okay, and after that we will be understanding the motion of charge. That is what? Motion of charge or the movement of charge, isn't it? That particular motion of charge is nothing but what we called electric current, isn't it? Okay, and thereafter its effects. Whose effect? The effect of that particular electric current. Clear? This is the simple map that we are going to follow. First of all, we will be understanding what is an atom, and thereafter we will be understanding what is charge. Thereafter we are going to consider the motion of that particular charge, that is the movement of charge, and thereafter we will be going with the effect of that particular current. Okay, so this is all what we are going to study in that particular chapter. Okay, please be patient while going through the lecture. So let us start with our chapter electricity. Okay, so in our earlier classes, that is in 8th, 7th, 8th and 9th standard, we have seen what is an atom basically. Okay, so let me give you a very simple idea regarding an atom. So see, in general, atom seems to be like this, isn't it? Spherical in shape. Okay, and this is the center of the atom. Okay, at the center, this center is what we call nucleus. This is what we call nucleus. At the nucleus, what we have basically a positive charge whose name is what? Proton, plus a neutral charge or no charge, that is what we call neutron, right? So proton is basically what? Positive, and it has no charge, that is neutron. Clear that much? Now thereafter, these are the orbitals. These are what? The orbitals of the shells, over which there will be some electrons. Okay, there will be electrons which will be moving around the particular nucleus. Is it clear? Now these electrons are negatively charged particles. These electrons are what? Negatively charged particles. Clear that much? Now, so out of this what you can conclude, that charges are simply the constituent particle, are simply the constituent particles of an atom, isn't it? So this can be a very simple in general definition. Okay, so these charges we are going to consider. Okay, see, in earlier days, scientists were unable to found negative charges. That means electron was far later discovered, that is after proton. Okay, so earlier what scientists used to do, scientists earlier used to assume that earlier positive charge motion was assumed to be the current. Okay, although after that the scientist has discovered electron, that is the negative charge particle. Thereafter our recent studies going on. Okay. So in this chapter, the charge, whenever I will be saying a charge, that means I will be giving a hint to negative charge only, that is the electron. Okay. So for your information, both electron as well as proton, both are having what? Charge of same magnitude, although both of them will be having different signs. Okay. So proton will be a positive charged particle, whereas an electron will be what? A negatively charged particle. So let us see the SI unit of charge. Okay. So what is the SI unit of charge? It is coulomb. Okay. And symbol will be what? Capital C. Clear that much? So what is the SI unit of electric charge? That is coulomb, and the symbol is what? C. Okay. Now see, charge on an electron, okay, will be simply equal to what? Minus 1.6 into 10 to the power minus 19 coulomb. Clear? Similarly, charge on a proton will be equal to how much? Plus 1.6 into 10 to the power minus 19 coulomb. So what we can realize from that particular, that the charge on both electron as well as in proton are what? Same. What is the difference? Difference is in their sign. Okay. So that electron is what? Negatively charged particle, whereas the proton is a positively charged particle. Now further moving with that concept of charge, neutron has no charge. Neutron has no charge. Okay. Now we will be trying to understand what is quantization of charge. Thereafter we will be moving with the definition of electric current. So let us see what is quantization of charge. This is also known as what? Conservation of charge. Okay. So quantization of charge. So what is quantization of charge? It says the total charge in any charged body is, suppose say capital Q, will always be equal to n times into E. So what is n here? N is simply equal to number of electrons. Here charged particles also you can say, and E is equal to what? Charge in an electron. So mostly I will be writing electron as e to the power minus, right? Clear that much? So what is quantization of charge? It says that the total charge in any object or in any charged body Q will be equal to what? N times of E. So let me describe this with a simple example. Suppose this is an object, okay, which is having a suppose total charge Q equal to 50 coulombs, say. Okay, so this is an object, say charged body. This is a charged body which is having charge equal to how much? 50 coulomb. Now according to the quantization of charge, if we split that particular charged body in numerous particles, okay, so there are 5 particles now. So this is 1, 2, 3, 4 and 5. So these are the pieces. Okay. Now if we combine all of these charged particles, the total charge by all of these 5 particles will be equal to 50 coulomb. Okay. Now see here, after breaking down this charged body, we are having n equal to how much? 5. Okay. And in each and every particle, right, the charge amount is how much? Will be simply equal to charge on an electron. That means the total charge Q will be equal to what? N into E, which will be equal to how much? N is how much here? 5. E is how much? The charge on an electron. So what is E? E will be here charge on an electron. Okay. Just for the sake of explanation, I am considering n equal to 5. Okay. It could be anything also. Clear? So please make a note up to now. Okay. Now we will try to understand the very basic fundamental definition of electric current. What is electric current? Okay. Whenever there is any term like current, we must have an idea of motion. Okay. Something which is in motion. That is what we call current. Okay. Here in our chapter, we are going to deal with electric current. So what is electric current? Simply, it is the movement of charge. Electric current is nothing but the movement of charge. So let us see what is electric current definition says. So the designation for electric current is what? I. Okay. So the definition says it is simply the rate of flow of charge. It says what? The rate of flow of charge per unit time. Per unit time in any area. Okay. Say rate of flow of charge per unit time in any area. From the definition only we will be trying to make up the basic formula for electric current. So what is electric current? That is I is simply equal to what? Rate of flow of charge. So the designation for charge is what? Q. Okay. Per unit time is what? T. Okay. So I is coming as what? Q upon T. So this is the basic fundamental formula for electric current. Okay. Which is equal to Q by T. Here Q is what? Our charge, or basically you can say precisely it is the net charge. Okay. Whereas T is the time for which the particular charge is flowing through a particular area. Okay. In general, in our wires, this is an electric wire. Okay. In that particular wire, what we are having, the cross-sectional areas, this and this, these are the cross-sectional areas. There are infinite number of cross-sectional areas. All these are what? Cross-sectional areas. Okay. And the cross-sectional area of that particular cylindrical wire, this particular wire is, the shape of that particular wire is what? Cylindrical. It will be always equal to what? Pi into r square. That is equal to area of cross section. Okay. So the term area of cross section has to be clear to you. Okay. For the better understanding, let us see. Say this is a marker, right? See, this is the length of the marker. This hole is the length of the marker. This part is what we call the cross sectional area of that particular marker. Clear that much? Now coming to the SI unit of electric current. SI unit of electric current is ampere. Is what? Ampere. And the symbol is what? Capital A. Clear that much? So now this ampere, this particular unit ampere in our numericals or in our problems, practical problems, will be very small in general. Okay. It will be in milli, it could be in micro as well. Okay. For the conversion of units, I'll just help you to make a note that 1 ampere is equal to, or you can say 1 milliampere is equal to 10 to the power minus 3 ampere. Okay. So this will be the frequently used unit of that particular electric current. Clear that much? So what we have learned, the concept of charge. Thereafter we used the definition of charge to understand what? Quantization of charge. Thereafter we have seen what is the basic definition of electric current and its basic formula from the definition itself. Okay. That is I equal to Q by T. And thereafter we have studied what is the SI unit of that particular electric current. Right. So now let us make a question. So let us frame a question. Say this is an electric wire. Say this is an electric wire. Okay. Which is having certain length. Say the length of the particular wire is what? L. Okay. There is certain current I which is equal to 10 ampere. Okay. Say this is my electric wire. Okay. Which is having a length of how much? Say L. In this particular wire, a certain current I which is equal to how much? 10 ampere. The value of that particular current is how much? 10 ampere, which is flowing across that particular wire. Okay. For the time, t equal to say 10 seconds. Clear that much? So in that particular wire, so the name of the wire is suppose A, B. In that particular wire, a current I equal to 10 ampere is flowing for time 10 seconds. Okay. What we need to calculate, or what we need to determine, calculate the net charge flowing in the wire. So this is our simple question. Okay. So how to solve this? See. So from the very basic definition of electric current, what we know is current I is equal to what? Q by T. So what is our target is to calculate the net charge, right? So here Q, which is our net, right? Here this Q net is what? Our net charge, which will be simply equal to I into T, right? Just simply cross multiplication of current into time is going to give us what? Net charge Q. So now the value of current I is given in the question only, that is equal to 10 ampere. For the time which it is flowing is equal to how much? 10 seconds, isn't it? So the answer coming will be what? 100 coulomb. So in that particular case, the observation is that in that particular wire, when a current of 10 ampere is flowing across that particular wire, AB is the name of the wire, isn't it? And the current flowing is how much? 10 ampere for 10 seconds across that particular wire. In that particular situation, the total charge or the net charge accumulated or the charge which is flowing across that particular wire is simply equal to how much? 100 coulomb. Clear that much? So please make a note of that. Okay, you can pause the video in that particular situation and you can make a note. Okay. So we have seen the basic definition of electric current, and we have solved a very simple numerical based on that particular formula of electric current, which was I equal to Q by T. Now we will try to understand what is an electric circuit is all about. Okay. So let us see what is an electric circuit now. Electric circuit. So what is an electric circuit? So let us see the definition. Fundamental definition of electric circuit says what? A closed and continuous. A closed and continuous flow of electric current. Of electric current is simply what we called an electric circuit. Now see, these two words are closed and continuous, isn't it? These two words, closed and continuous, these are the mandatory, right? These are very mandatory things that has to be there in the definition of electric circuit. So that means an electric circuit is simply a combination of what? A closed and continuous flow of electric current. Okay, that is what we call an electric circuit. So in general, an electric circuit seems to be like this. In general, an electric circuit seems to be like this. So this is a resistor. I will be describing all of these particular electrical appliances for now. Let us see only. This is an electric resistance R. Okay. Say this is an electric bulb. Okay. Now these are the wires, right? All the straight lines are simply what? The connecting wires. Okay. Now this is an electric cell combination. This is a simply electric cell combination. That also you can say what? A battery. Clear? Now this is a key, and that particular symbol means what? A closed key. Unless and until the circuit is closed, there won't be any flow of electric current across that particular circuit. So this is a very simple component of an electric circuit here. This is our resistance. This is what? Our electric bulb. This is what? An electric bulb, isn't it? These are wires, connecting wires. Okay. All these are of metals. Okay. This is switch or key, and this is what? A battery. So battery is simply the combination of cells. Okay. Now all these electrical appliances we will try to understand first. Okay. So let us see different electrical appliances that we will be using in our upcoming topics. Different electrical appliances or components as well. Okay. Appliances or components and their symbols. So let us see. So number one, this is what you call a resistor. Okay. R is the resistance here. Okay. So the symbol for the resistor is what? This is what? A resistor. Okay. So this is the symbol for resistor. Sorry. This is the electrical appliances. Okay. And the symbol is going to be what? Made a very silly mistake, sorry. This is a resistor and this is the symbol of that particular resistor. Okay. Next is suppose cell. Okay, so a cell normally in general seems to be like this. Okay, it is having two terminals, one is positive, another one is what? Negative. Okay, so this is a symbol for electric cell. Then let us see what is battery, how it seems to be. Okay, a battery seems to be like this only, combination of different cells. Okay, so this is the combination of different electrical cells. Okay, clear? Now see, always the longer terminal is going to be what? Positive, and the smaller one is what? Negative. Okay, next, variable resistance or resistor you can say, and the symbol will be simply like this. Okay, so this is the symbol for variable resistor. Then electric bulb. Right. So this is the symbol for electric bulb. Okay. Then switch. Switches will be in two modes. One will be closed, another one is open. So this is a closed key, okay, and this is an open key. This is closed and this is open. Okay, open means what? When there will be no flow of electric current, that sort of electric circuits are what you called open. Okay, and what is closed? When there will be certain flow of electric current across that particular circuit. Clear? So further moving with components. So we have seen what? Electric cell, electric battery, variable resistor, electric bulb, electric switch. Thereafter let us see wire joints. Wire joints. Okay, so this will be a simple designation, simple symbol for electric wire joints. Okay, when wire will be overlapping each other without any joint, okay, it will be symbolized as wire overlap without any joint. Without any joint. So let us see. So see, this is a simple two electrical wires which are having no joint, although they are overlapping each other. Clear that much? So these are very simple electrical appliances that will be frequently used, that we are going to frequently used in our upcoming topics. Okay, so let us go through with all of these component once. This is a resistor and the symbol for resistor is this one. Okay, this is an electrical cell. This is the symbol for electric cell. This is a battery, which is simply the combination of different electric cells. This is a variable resistor. This is an electric bulb. This is a switch. This is wire joints. This is wire overlapping each other without any joint. Clear? That all these basic stuffs we will keep in our mind. Okay, for our upcoming topics. Now we will be starting with the concept of electric potential. Let us start with the concept of electric potential. So before understanding the concept of electric potential, let us try to understand what is the literal meaning of the term potential. Okay, and one more very important and very frequently used in general term, that is what? Infinity. Okay, so let me explain two terms first. Okay, first is what is infinity, and second is what is potential. Okay, so let us say these are the 2 points. So this point is x, this point is y. This is a point x, this is a point y. Okay, say at point x there is a dog. Suppose there is a dog at point x. That particular dog is going to move from point x to point y. Okay, now the new position of the dog will be there only, right? Clear? And the distance between the points x and y, is suppose 100 meters. How much it is? 100 meters. Okay, try to understand. There are 2 points x and y. At the point x there was initially a dog. After certain time it is supposed to cover a length of 100 meters so that he can reach point y. Okay, clear? Now see, in general a dog can have hardly a length of how much? 1 meter. Let the length of that particular dog is suppose 1 meter, although 1 meter in general the dogs are not of having length of 1 meter. So we are supposing here in that particular case that particular dog is German Shepherd. Okay, So the distance between the point x and y is how much? 100 meter, and the length of the dog is how much? 1 meter. So in this situation, when the dog will be covering a length of 100 meter, and when we will be comparing the distance covered by the dog to his own length, which was what? 1 meter. So what we can say, that 1 meter is simply much lesser than 100 meter, isn't it? So whenever a particular object, in that situation our object is nothing but dog, right? Whenever an object will cover a certain distance or a certain length which is much higher than its own length, then in that particular situation we will be calling it an infinite distance. Infinite distance. So in this case the dog has covered an infinite distance. Why? As compared to his own length, the distance covered by him is much more greater. Clear that much? So this particular term infinity or infinite will be frequently used in this particular chapter. So although for this particular topic of electric potential, we will try to understand what is that particular infinity is all about. Okay, clear? Let us take one more example. Suppose this is again point x, so this is again point y. Okay, so there is a charge, say a charge q is at the location x. Now we are taking the particular charge q from x to y. So we are taking the charge from x to y. In that case, we know the charges are very small, right? We cannot see any of the charges with our naked eyes, right? That means the size of the charge is very small, and whatever be the distance it has covered will be what? Much higher than its own size or its own length or its own dimension, isn't it? So in this situation also it has covered a distance of infinite. Again the charge has covered a distance of what? Infinite. I suppose all these are very simple concepts are clear to you now. Okay. Now let us try to understand the concept of potential. Mind you, this is not electric potential. I will be briefly explaining what is electric potential although. So let us first of all try to understand what is potential simply. Okay. So the term potential means what? Suppose we want to calculate the potential of any object, isn't it? So how to calculate? Suppose there is a marker on my hand, right? I want to calculate the potential of that particular marker. So how to calculate the potential of that particular marker? To calculate or to determine the potential of that particular marker, I need to do some work on that particular marker. Okay, and the amount of work I will be doing on that particular marker will depend on the capability of the marker, not of me. Try to understand what I mean to say. So there are two cases. In the first case, I need to take that marker from this point to this point. Okay, from my right hand to my left hand, I need to move this particular marker. So while doing so, I am doing certain amount of work, isn't it? Now in the second scenario, what we are doing, I am considering a mobile phone on my right hand. Okay, in that situation I will be taking that particular phone from my right hand to my left hand. While doing so, again there is certain amount of work that I am going to do, isn't it? So what is the difference in between the two cases? The work I will be doing in first case will be automatically lesser than the work I need to do in case of the mobile, isn't it? So why it is that the amount of work in case of marker is lesser? It is due to its potential. Try to understand. It is not my potential. It is the potential of marker. Similarly, it was the potential of the mobile, which is bounding me to do work according to its capability. Okay, clear that much? So potential is simply means what? Capability or capacity, isn't it? So these are very simple terms we will be using in our topic of electric potential. So I guess all these concepts are very much crystal clear to you, right? So let us see what is electric potential. So electric potential is always for a point we are going to determine. Okay, electric potential is always going to be determined for any particular point. So let us try to understand what is electric potential. Electric potential, let us see. The symbol for electric potential is what? Capital V. Clear? So what is electric potential? Say there is a point P. Say there is a point P. I need to calculate, or I want to calculate the electric potential of that particular point P. For that, how to calculate? For that, what I will be doing? I will be taking a charged particle. Say there is a charge Q. Say there is a charge Q that I will be taking from a certain point And what is the particular starting point? That is infinity. And what is infinity? That whatever be the distance the charge is going to cover will be what? Much higher than its own dimension. Clear that much? So I am assuming that I am taking up a charge from infinity. From where? From infinity I am taking the particular charge up to the particular point P. While doing so, I am doing what? Certain amount of work. And the amount of work that I need to perform while taking that particular charge from infinity to particular point P, that is simply the potential of that particular point P, not the potential of infinity. Try to understand. Let me tell you once again what we are going to determine: electric potential of any particular point P, right? While calculating the potential of particular point P, what we are doing, we are taking up a charge, electric charge, right? And we are moving that particular electric charge from infinity to a certain point P, right? Which point P? The point about which we are going to calculate its potential. Clear that much? So for that particular movement of that particular charge Q from infinity to P, we need to perform certain amount of work. So the definition of electric potential says what? It is the amount of work. It is the amount of work need to be done to move a charge from infinity to that point. What is that point here? That point is simply the point P. I guess this is very simple and clear, crystal clear to you people, right? So it is the amount of work need to be done to move a charge from infinity to that particular point, right? So here that is electric potential V is simply equal to what? From the definition C we are going to generate the formula, right? So we are doing certain amount of work, isn't it? Let that particular work is what? W, to move a particular charge what? Q. In that particular case, what is our charge? It is simply capital Q. Clear? So the basic formula for electric potential is what? V, which is equal to what? W by Q, where W is what? Our work done, whereas Q is what? The charge that we have taken from infinity to particular point P. Clear that much? So there must be a point you should remember. Okay, so you can make a note like this: electric potential of infinity is always zero. See, in our syllabus there is no scope why the electric potential of point infinity is zero. Okay, so all this will be, you people will be getting in your class 12 standard physics. Okay. So for the time being, you just keep that particular statement in your mind, that electric potential of point infinity is what? Always zero. Clear? So next, SI units. Okay. So the formula for electric potential was what? V equal to W by Q. So V equal to W by QC. The SI for work done is how much? What? It is simply joule, isn't it? And what is the SI for charge? It is coulomb, isn't it? So the SI unit we are going to get is what? Joule per coulomb. So simply we can write, this is joule, this is coulomb, so it will be joule per coulomb, isn't it? Or SI unit of electric potential is also volt. Is also what? Volt. So that means 1 joule per coulomb is also equal to what? 1 volt. That you must keep in your mind. So there are two units that we are going to use for the term electric potential. Number one is what? Joule per coulomb, or simply volt. Clear? So 1 joule per coulomb is equal to what? 1 volt. So let us try to understand what is the meaning of term 1 joule per coulomb. So 1 joule per coulomb means what? 1 coulomb, right? So while moving a charge of 1 coulomb, what we are doing? We are performing an amount of work which is equal to 1 joule. Okay? So these are the literal meanings, and all the significance we will be trying to understand in our next topic, which is what we call electric potential difference. Clear? So for the timing, just make a note of all this.